I'm from Texas, a school called West Texas A&M University. We're actually in the north part of Texas. The region is actually very agriculture intensive region. Okay, the Texas, Oklahoma, Colorado, a lot of states, New Mexico, that fourth state region, we call it Texas Panhandle. It's a very agriculture intensive. Let me tell you, for example, the American people, you know, really like the beef. You eat a lot of beef. More than one sort of beef comes from the Texas Panhandle. The intensive, you know, agriculture, you know, concentrated feeding operation can create a lot, you know, generate a lot of beef for the consumer. That's why we're interested in agriculture. And this project, one of the projects, you know, I get from USDA, trying to say, okay, in food safety inspection, how can you quickly detect bacteria in the food? That's actually a big challenge. Let's take a look. You know, first I'm going to give you, you know, very brief introduction and you know what is, you know, Salmonella, and you know it's a challenge. How do you detect the bacteria in the food? So then we're going to take a look what is immunomagnetic separation, that technology, and the challenge use that kind of separation in food sample analysis. We did a little bit of work on this. I would say it's very preliminary, okay? And then we're going to take a look, you know, for what we want to do. Take a look. Here's the Salmonella, that kind of bacteria. And now Salmonella is one of the bacteria in food, you know. A lot of one you probably hear sometimes called E. coli. Okay, that's also very dangerous stuff. According to, you know, CDC, US CDC website, each year in this country, among 19,000 infections, around 400 people died from it. So it, you know, is the issue. You know, Salmonella infection usually this one related to the bird, the poultry, and the egg product. Okay, that's not much related to the beef and the cattle, animal, you know, mostly related to the bird. So the quick detection of Salmonella contamination is really challenging. We're going to show you, you know, some of, you know, the method, you know, traditional method how to do this. One example, I can see that, you know, 2 years ago, I think 2 years ago, one company in Ohio, egg producer, okay, that company exists for more than 6 years. Two years ago, they had a major Salmonella contamination in their egg product. The quantity of egg contaminated is so much, the company cannot pay the money for record the product. The company have no way to announce bankruptcy, out of business. That, you know, you can see the cost of, you know, Salmonella contamination. Now, how to, you know, the challenge detect, you know, this kind of bacteria in the, you know, in the food sample. That's a big challenge, you know, sensitivity requirement. It was told that some of the bacteria, you get, you know, Salmonella, certainly depend on people. Some people are strong, some people are a little bit weak. If you get 10 to 100 bacteria into your stomach, it can kill you. 10 to 100 bacteria, very small. And you have, you know, some just bacteria grew. You have one bacteria that grew. They're not migrate, move around. They just grew in. So if you have a sample that's big, you only have this place you have your bacteria. You take a sample here, you miss it. You know, that's a lot of issue. When you analyze the sample, it's a big issue. Complex sample matrix, you have a lot of different stuff. Now, if I compare this to, you know, one thing, you know, how difficult it is to you know, detect the bacteria in food. If you compare this to, for example, several years ago, we tried to hunt Bin Laden, the terrorist. You hunt one person on the whole planet, on Earth. How many years we spent to finally get him done? This is more difficult than that. This is more difficult than that. Say you detect one, you know, 10 bacteria in how many molecular? One more is 6.02 to 10 to the power 23 molecules. So you can see, you know, how big is that problem. Also very complex, you know, you don't know where it's related, okay? So because that kind of difficulty right now, traditional method. What do we do? Detect the bacteria. But first, try to increase the number. First, put the sample. You take the sample, put the sample to a broth solution, and let them grow. Okay, one bacteria become 2, 2 become 4, 4 become 8, and after 2 or 3 days, you get millions or billions of that kind of bacteria in your sample. That's where you grow the lumber. After you grow the lumber, then you put the solution in this kind of period dish. You have growth media, selected growth media. Inside that solution, still have a lot of different bacteria. So this media help you only grow Salmonella, or a lot of media only grow the E. coli. Okay, you can selectively grow your bacteria. When the bacteria breathes, during the time the group breathes, generate hydrogen sulfide. So in that kind of media, they put some kind of iron ferrous compound there. So hydrogen sulfide come out, react with the ferric ions that give you ferrous sulfide. That give you the black color. Okay, you count how many colony you have, say how many bacteria you have. That to do the calibration, certainly you have a calibration process. So take a look how many times you need, this process. This group process costs, you have 2 or 3 days. Here you have 1 or 2 days. You have a doubt something is there, and then you need to confirm that. So normally you need 1 week to do this. 1 week, during that 1 week, the product is already on your desk. You already eat it, okay? So sometimes it causes a problem. That's why, you need a quick detection. If you have a quick detection technology, you can get it done before you put the product on the market. You do not need avoid the recall. Now, here comes the material science part. Immunomagnetic separation. What that kind of technology looks like. This one, for material scientists, probably is very easy. Here you first have the paramagnetic particle synthesizer. You put a ferric oxide, ferrous oxide synthesizer in. Even if you want to make perfect ball shield, you can use material technology to do this. So make the ball particle, and the magnetic particle you coat. After you make the magnetic particle, you coat on the surface of the magnetic particle with a polymer. Okay, you do coating, coat on this kind of PMMA or polystyrene, that kind of polymer. On the polymer, give some new Hawk, site. You can bond that with the antibody. Okay, through biochemical reaction, you can bond that with the antibody. So then you can have a lot of this kind of particle you can put in your sample, and the antibody will trap the bacteria. So you spread it out, like you spread it out to your sample, that will trap your bacteria. Now, after you trap your bacteria, what you can do, you can put a strong magnet, like this kind of thing, strong magnet, to pull out the magnetic particle. In the same time, you pull out the bacteria, and you dump all the sample. This is just like if you see the bin Laden virus, you can put the magnet, pull bin Laden out, and you can arrest him. Because that's the way, looks like a perfect method to do this kind of things. It is true in biology, biochemistry research. Say you have a very small quantity of sample. Remember in biology, people handle solution milliliter or microliter. That kind of separation will be very perfect to do it. But when you're trying to test your food sample, you have hundreds of grams of your sample. You only have milligrams of this kind of particle put into your sample. That's actually a challenge. It's not easy to do it. So here, the challenge to use, immunomagnetic separation for food safety. You have limited sample size, and that's related to your homogeneous sample distribution. Your sample, as we said, the bacteria might be here. You take the sample here. That's a problem. Okay. Separate magnetic particles. Remember the magnetic particle inside the micrometer range. That if in chemistry we know that colloidal precipitation. Colloidal precipitation is very difficult to set out. Okay, even you use strong magnet, Even use a strong magnet, still take time to separate them. Okay, and now right now in biology, we use a lot of optical technology. Now with optical technology, we can detect even a single molecule. That's possible. We can do it. The problem is the magnetic particle. You have a lot of interference, optical interference. It's very difficult to detect. Directly use optical technology to detect it. That's one problem. Okay, so let's take a look. How do we do this? Here is we test raw egg, not a cooked egg. Raw egg, very sticky, high viscosity fluid. So the raw egg, if you just put your magnetic particle to it, very difficult to distribute the magnetic particle to the sample. So what do we do? Well, first, put the raw egg, break the egg through out the shell, and the egg homogenize. Use a blender. Put some Triton X100 to try to decrease viscosity. Then you put the compound you can buy it from, I think, Life Science Technology. That company sells the magnetic particle that is coated with anti-Salmonella antibody. Okay, we put 1 milliliter of that kind of solution into here, roughly 200 milliliters egg solution. So you just use a glass roller to mix them and then let them to stay for roughly 45 minutes. So during that process, the bacteria is bound with the antibody on the surface of the magnetic particle. Then you put another big magnet here, just like shown here, roughly 1 inch strong magnet. Be very careful. That's very strong force. If you put two together, it can break your hand. so put that one inside a plastic bag. Okay, put it inside zip bag. Put the magnet, and you use a metal wire to stick to the magnet. That will stick the magnet like this, and stick the whole thing into the solution. The magnet inside the plastic bag. Then the magnetic particle will stick on the surface of the plastic bag because of force from the magnet. Okay, and after 90 minutes, you pull out the magnet with the plastic bag, zip bag. Okay, then you take out the magnet. Take out the magnet. Then there's no force to trap the magnet. You can use water to wash out the nanoparticles, the magnetic particle from the plastic bag. Then to solution, then you can handle the solution. So from that, we can transfer the solution to the magnetic tube. Now remember, the bioreaction is more complicated than what we expect. You think about the antibody only selectively pick up that kind of bacteria that actually pour out more proteins, that kind of things on the surface of the magnet. So you need to go through a cleaning process, intensive cleaning process. So we're going to clean with the PBS buffer for 3 times, clean the particle, and then finally we put BSA, that kind of protein to block the surface of the magnetic particle, which it might trap other bacteria or protein, that kind of thing, block it. So on the surface, what you have the bacteria, the other side, you basically blocked with the protein. Okay, then you put another antibody. That antibody stick on the surface of the bacteria. Now that antibody on the surface stick with the enzyme, and that enzyme, you have some material to it that are going to react, cause the color change of the solution. You put a substrate for that enzyme, so that will cause change the color of the solution. You can measure use light absorption to measure the color. You see how much color change. If you do a calibration, you can see how much bacteria is trapped onto the surface of the magnetic particle. That's the whole process. Now, this whole process, roughly 5 hours operation. 5 hours operation instead of 1 week. Okay, so in time, this one still, pretty fast. Also, 5 hours operation, my student get tired of this, but still, compared to, traditional microbiology process. Take a look, here are the test results. We say, here we use final, measured absorbance signal to say the conditions, how much time we need to incubate the magnetic particle with the sample solution, roughly about 40 minutes should be enough. So we incubate, that's normal optimization process. And here are the magnet, M50 magnet, how long time you need to stick here, roughly in more than 1 hour. So still pretty, long time, this process than what we expect, okay? So here is we do, the enzyme tagged antibody, how much we need, you do not need much, 1 microgram, milliliter solution. Now, also we do not need much solution. Remember, this kind of solution, the bioreagent is very expensive. Bioreagent very expensive. 1 milliliter solution normally costs you $200 somewhere. So this is actually a lot of challenge for the farmer. For the farmers, if you want them to use your technology, they probably do not want to pay so much money to buy the reagent. That's a lot of challenge. Okay, here's the calibration. We can, detect how much. Here, detection limit. We can detect roughly 14 million bacteria. Okay, that's still a lot. If you get that much bacteria to your body, it kills you. Okay, we can detect, still not enough. As I said, the goal for us is trying to detect single-digit number of bacteria, but this is still not enough. Or in solution, now this one detection limit is actually pretty good. If in single, 1 milliliter solution, this can detect roughly 70,000 bacteria in 1 milliliter solution. Also, this one not reached my goal yet, but the detection limit we achieved still the highest among the methodology, reported on the literature. So that's, still pretty good. So anyway, here take a look. We can use immunomagnetic particle to separate Salmonella from rogue egg. It is a very difficult task, think about things. And, you can achieve this analysis within 5 hours. That's still pretty good, pretty quick. Detection limits, now this one still not as good as I had expected, but it's still pretty good. So now the problem here, difficulty is to separate, take time to separate the magnet particle from the solution. That's one thing. And stir the solution. Now, right now in the solution, if you can stir the solution, probably you can accelerate the reactions. The problem is right now all the stirrer are magnet stirrer. If you use magnet stirrer, your magnet particle stick on it. We're trying to get a mechanical stirrer and use plastic blade to stir it. But that kind of stirrer right now, most stirrer are used for industrial operation. Very big. It's not used for laboratory use. That's one thing, give us. Actually, we can, we can try to increase the sensitivity with fiber optic technology. The original methodology I tried to propose is use a special fiber we call liquid core waveguide. That means a Teflon tube, a special Teflon tube. If you inject a solution in the tube becomes an optic fiber. So that means how long tube use, you have how long, just like in UVS absorption, the sensitivity is proportional to the path length. You use 1 centimeter or 2 centimeter sample cell, you have increased sensitivity. So if you can use meters of that kind of fiber, you can have a higher sensitivity. You can detect much, much more. The problem we had here is that we got a blank here, blank signal, pretty high. That's the problem. So we use 1 centimeter sample cell, you have 0.04. That means if I use 1 meter, I get 2 meters sample cell. That absorbance value will be 4. What that means? That means 99.99% of light is absorbed by the blank. So you cannot get very good, detection. That's why one method, not working very good. Now, we're trying to do, a different approach to do this. Here's what I'm trying to do. I'm using an optic fiber. Here is the optic fiber. And I can coat the antibody on the surface of the fiber. We achieved that recently in the lab. Coat the antibody on the surface of the fiber. And then I can put, use that fiber to pick up the bacteria from solution. Now, in this time, you can stir the solution with the magnet stir ball, accelerate the reaction. Okay? Then you can use a lot of antibody which is tagged with a fluorescence compound. Okay? You can use the fluorescence immunoassay. You can do that. Then you can use a liquid cold waveguide to excite the fluorescence compound on the, on the surface of the fiber. And the light fluorescence or the reaction, emission, we know that the optic fiber pick up the fluorescence. You can send that to fluorescence light pick up by the fiber to a detector. You can easily detect that. Now, recent work in my lab, I do not have a chance to put this here in this presentation. We achieved roughly 1,000, molecular detection. Okay, I showed 1,000 molecular detection. So that's the next step. We're going to, work on that. So that hope that will give us better chance. As we see that this work is supported by USDA, National Institute of Food and Agriculture. Thank you for your attention. I'll be glad to answer any question you have.